In this lesson, we will look at the components that are used for the control, protection and monitoring of an aircraft's AC electrical system. We will also look at the sources of backup and emergency electrical supplies. In order to see how a typical parallel generator system is controlled and monitored, we will look at the layout of a 3-generator parallel system. Notice that for each of the 3 phases of the output, there is a separate bus bar. For example, the number 1 generator bus bar, Gen Bus 1, is made up of 3 separate bus bars, A, B and C, for phases A, B and C. These bus bars are often referred to as the load bus bars, and all the electrical loads of the aircraft are shared between them. Each generator is connected to its own generator bus bar through a 3-phase relay, known as the generator circuit breaker or generator control breaker, GCB. The GCB can be operated automatically or be controlled from the flight deck. In the system shown here, close and trip switch lights allow the pilot to control the GCB. Visual indication of the position of the generator circuit breakers is given by indicators on the electrical control panel or the electronic display panel. A number of different annunciations are used. In the system shown, the flow bar in the close switch light is illuminated when the GCB is closed, and open is illuminated in the trip switch light when the GCB is open and the generator is disconnected from the bus bar. On some aircraft types, opening of the GCB also causes the centralized warning system to operate, and there may also be an aural warning. To operate the generators in parallel, they are connected through their respective generator bus bars to a synchronizing bus bar by bus tiebreakers or BTBs. A bus tiebreaker is a 3-phase relay, very similar in construction to a generator control breaker. And again, it can be controlled automatically or manually from the flight deck. Automatic control of the BTBs is provided by a synchronizing unit. The synchronizing unit monitors the phase sequence, frequency, and voltage of the synchronizing bus bar and the generator to be paralleled. It will only allow the BTB to close when the correct paralleling conditions are met. The synchronizing bus bar has no electrical loads connected to it. Its purpose is to allow the engine-driven generators to be operated in parallel, to allow another generator to power a failed generator's load bus bars in the event of a generator or engine failure, and to allow an external power supply or power from the APU generator to be fed to the load bus bars through the bus tiebreakers when the engine generators are not operating. In a modern generator control system, the generator control unit, or GCU, is the component through which most functions of a generator's control and protection are provided. A GCU is provided for each generator. A typical GCU will monitor generator output and provide voltage regulation by controlling the exciter field current. The GCU contains protection circuitry, which will monitor for over and under voltage and frequency, and incorrect phase sequence. In the event that the generator has an under voltage fault, or an under or over frequency fault, the GCU will open the GCB, disconnecting the generator from the bus bar. The GCU also contains a relay, known as the exciter control relay, generator control relay, or generator field relay. This relay controls the exciter field current supply to the generator field. If the generator develops an overvoltage or overexcitation fault, that is to say, if the output voltage or the field excitation current flow becomes excessive, the GCU will open the exciter control relay. This will cause the generator output to fall to a residual value. It will also open the generator control breaker to disconnect the generator from its load busbar. The generator control units may work together with a component known as the Bus Power Control Unit, or BPCU, to monitor the entire system for differential current faults. Differential current faults are short circuits between busbars, or between a busbar and earth, causing unbalanced phase currents. The GCUs and the BPCU monitor current flow in each generator and busbar. They will isolate a defective generator or faulty busbar by opening the appropriate GCBs and BTBs. So a short circuit on number 1 generator busbar would result in number 1 GCB and BTB both opening to isolate the faulty zone. And a short circuit on the synchronizing busbar would cause all 3 BTBs to open, again isolating the faulty zone. Each generator will now be supplying its own busbar. Load meters are used in parallel generator systems to indicate the generator real or true power and reactive power output. There is normally 1 meter for each generator. Typically, the system is configured so that the real power in kilowatts or kW is normally displayed. Pressing the button allows the reactive load in kilovolt amps reactive or kVAR to be displayed. Modern electronic display units may only show the load as a percentage of the maximum permissible load. Others don't have load indicators, with load shedding happening automatically if the load limitations are exceeded. A method of checking the voltage and frequency of each generator is usually provided. In this typical system, the voltage and frequency of any generator can be monitored on the meters by selecting the generator to be monitored on a multi-position switch. The switch can usually be positioned to show not only the supply frequency and voltage of the engine-driven generators, but also that of any other AC supply that may be available. On most modern aircraft, this information is available to the pilot on one of the electronic screens. In the event of some or all of the engine-driven generators failing, possibly because of multiple engine failures, alternative methods of supplying AC for essential services must be made available. The most commonly used methods are the ram air turbine-driven generator, the auxiliary power unit-driven generator, the hydraulic motor-driven generator, and the static inverter. The ram air turbine, or RAT, is a propeller-driven device which can be lowered into the slipstream when required. If fitted with an AC generator, it will produce an emergency source of AC power. It may be known as an LRAT. On many modern aircraft, the ram air turbine is used to drive a hydraulic pump, rather than an electrical generator. The auxiliary power unit, or APU, is usually a small gas turbine engine, normally mounted in the aircraft tail cone. This engine runs at a constant speed, and has automatic protection devices which will shut it down in the event that it develops a fault. It can be used, amongst other things, to drive 1 or 2 AC generators for ground operations prior to engine start, or, in some aircraft, for emergency electrical supplies in the air. Because the APU runs at a constant speed, its generator does not need to be driven through a constant speed drive unit. The APU generator cannot normally be paralleled with the engine-driven generators, and can be only connected to the bus bars when no other source is feeding them. Some aircraft have a hydraulic motor-driven AC generator, which can be used to supply electrical power in the event of a multiple engine-driven generator failure. As with the ram air turbine-driven generator, the hydraulic motor-driven generator is normally only used to power essential flight instruments and radios, in the event of a total generator failure. A static inverter is a solid-state device, which converts DC into AC. It is capable of supplying the aircraft with 115/200 volts, 400 Hz, 3-phase AC, for the limited operation of instrument and radio services. It is powered by the aircraft batteries, or from an essential DC bus bar. On the ground prior to engine start, electrical power can be supplied to an aircraft by a ground power unit. The standard modern ground power unit output is 115/200 volts, 400 Hz, 3-phase AC, the same as the engine-driven generators. Ground power can be used to supply all the aircraft's electrical loads. The ground power unit circuitry must include automatic protection systems, which will ensure that ground power cannot be connected to the aircraft distribution system if the system is already being supplied by its own generators, that it cannot be connected if the phase sequence of the supply is incorrect, and that it will be rejected and switched off at source if an overvoltage fault occurs. That is the end of the lesson. The following are the main points you should take from it. Each generator is connected to its own bus bar through a 3-phase relay, known as the generator circuit breaker or generator control breaker. To operate the generators in parallel, they are connected through their respective generator bus bars to a synchronizing bus bar by bus tie breakers or BTBs. The synchronizing bus bar has no electrical loads connected to it. A generator control unit, or GCU, will monitor generator output and provide voltage regulation by controlling the exciter field current. The GCU contains protection circuitry, which will monitor for over and under voltage and frequency and incorrect phase sequence. If the generator develops an overvoltage or overexcitation fault, the GCU will open the exciter control relay, causing the generator output to fall to a residual value. The GCUs, in conjunction with the bus power control unit, protect against differential current faults. Alternative methods of supplying AC power are the ram air turbine driven generator, the auxiliary power unit driven generator, the hydraulic motor-driven generator, the static inverter, and on the ground power unit.